And good morning, ladies and gentlemen. Welcome back to the Simkins Physics Corner. I'm your host, Mr. Simkins. Today, AP Physics Simple Harmonic Motion. We're going to talk about springs and bobs. So there's a spring and there's a bob, a sponge bob. Not copyrighted for this video, but it's for educational purposes. So let's jump into it. What is a simple harmonic oscillator? Well, simple means it's not that complicated. Harmonic means it going back and forth in a certain pattern. And oscillating means that going back and forth. So simple harmonic oscillator. Let's look at some examples of some things we might see. The first type of simple harmonic oscillator we might see is something called a horizontal spring. That's like if I were to get something attached to a spring and pull it back a certain distance and then let it go boing, boing, boing back and forth. You can see that this mass here, M, is at this initial position right here. And if it's attached to a spring that can both be squished and stretched, all right, the spring can store energy in both directions. If I pull this mass over here and then let it go, you guys would all, oh, as I pulled it over there, I'm storing energy in the spring. The spring's going to say, nope, come back this way. But then eventually it's going to go over here and the spring's going to say, nope, come back this way. And what you'll have is this back and forth or oscillating motion. That's a horizontal spring. And you might also see something like a vertical spring, where if you have a mass dangling from a vertical spring, if I take that mass and I allow it to just kind of come to rest there, or maybe I pull it down a little bit or I drop it. We actually saw this with the egg drop lab that we did. But that spring, of course, if it's stretched out, it will pull up on the mass, and so that will cause it to go up a little bit. And then as the spring is getting shorter, it's not pulling as hard, but gravity is like, hey, come back, and so the bob will go back down again. And what you'll get is this up and down oscillation, or this spring bouncing up and down. Give you a quick example of something this might look like. Let's say I have this spring. This spring is a pretty stretchy boy here, and I take some mass and I put it on that spring. And if I do that, it's going to go, it's going to bounce up and down. This is called a simple harmonic oscillator. All right. And this will have a certain period associated with it. Period means the time it takes to go back and forth once to complete one full cycle. And so this is the first type of oscillator we're going to see is a spring oscillator. I don't have a good compact example of one that goes back and forth like a horizontal oscillator, like the aforementioned example that I gave, this one right here. But if I did have something like that, it would just go back and forth, back and forth, back and forth in the same manner, just flipped 90 degrees there from that original one. So let's consider what factors would impact how long this takes. What if we could derive an expression for the period, big T, that's the time it takes, that's why it's a big T, of a spring oscillator, the period of a spring oscillator. Now, it turns out that there's going to be some magic coefficient, and it turns out for this one that it's 2 pi out front. You probably would not have guessed that one off the top of your head unless you really know your oscillating functions very well. That actually has to do with the circular nature of a repeating motion of a circle, and we're kind of translating it into this one-dimensional motion. But I digress. Let's consider the factors that would come into play for a spring oscillator. Well, each spring will have a different springiness, or we call this the spring constant K. You can see this spring doesn't take a lot of effort for me to stretch it out, whereas this spring actually takes quite an amount of force. You can see it's a more tightly wound spring, and we can see that demonstrated too if I put a mass on it. You see how this spring hardly moves at all with the same amount of mass. If I put that mass over here on this spring, that spring is going to move back and forth quite a bit, and you can see that it takes a lot longer for this mass to complete one cycle when we have a stretchier spring, or a spring that is not as tense as this one. So of course that spring constant, we call that K, is going to come into play, and that's why when you look at your equation sheet, you probably wouldn't have guessed the square root, but you probably would have guessed the inverse. In other words, the period, or how long it takes, is going to be inversely related to how stiff your spring is, right? The stiffer the spring, it means a shorter period. That's why if the K on that bottom, if this number were to increase, the period would decrease. Why? Because you have a stiff spring. It's just going back and forth very quickly. Whereas if you had a very loose spring with a small K, a small coefficient, or a small spring constant, then that period would be a lot longer. So that's the inverse nature of the period of the spring oscillator and the spring constant. Of course, the other thing then is if I took this mass we saw with this pretty stiff spring, it hardly moves at all, right? Well, what if I double the mass? What if I take another 50 grams and I put it on this 50-gram hanger? Well, you can see now that it's taking longer to go up and down, bounce back and forth, That's because we increased the mass. And of course, any larger mass is going to take more time to change that mass's direction with F equals ma in this case, right? So that mass, as it increases, the period is going to be longer because we have to get this big mass moving, and then we have to slow it down and turn it around, then we have to get it moving again. And so that's where that equation comes from on your equation sheet for the period of a spring oscillator. Now let's talk about a pendulum, all right, a pendulum. So I have some string here, and if I tied my knot correctly, maybe I can get this thing to go back on here. A simple pendulum is one that has a simple mass attached to it from some certain length, maybe something like this, and it just goes back and forth, oscillates back and forth like this. Now you notice I didn't lift the thing like up here and go, whoa, because that's not a simple pendulum, because we're going to lose a lot of energy if we have a large displacement angle. So if you look at that diagram I have on my slide, a simple pendulum is usually defined as one that has a small angle that it's released from, like this. All right, it's a generally small angle. How big of an angle? I'm sure there's a number out there, but it just has to be a small one, all right, not a ridiculous one. And why not? Because if you go at some huge angle to start, you're probably going to lose energy as you swing back and forth a lot more at a higher rate. So that's why a simple pendulum or an ideal pendulum is one in which we release it from a small angle. So you can see the pendulum is going to have a couple of factors coming into play here. There's going to be how long is the string that I attach my mass to, or how long is the length of the pendulum. And then, of course, there's going to be how heavy is the thing that's hanging from the end of that pendulum. Now, you might be tempted to say, if we consider, all right, well, what does the period of a pendulum depend upon? All right, we'll drop this 2 pi in front of there again, because that's just the way it goes. I'm sure there's some fun mathematical derivation that I don't care to get into right now for you. But what factors would come into play? It turns out there's a square root again. Again, I'm not going to get into the details of that math, but let's just think conceptually. What would the period of a pendulum depend on? Now, a lot of people are fooled into thinking that if you put more and more mass on this thing, maybe that changes the period of the pendulum. Turns out that's not the case. It's very interesting, and you can do this pretty simply. All you need is to take a string, maybe a paper clip, and start hanging some washers on there, and you can keep releasing it from the same angle and time it. I dare you. Go ahead and do it. If you do it, you're going to notice that even if you put a lot of weight on there or not that much weight on there, it's going to take the same amount of time to swing back and forth. So the period of a pendulum, counterintuitively a little bit, is not mass dependent. You can test it out for yourself. I have a swing set in my backyard. If I put my son on there, or who weighs about 35 pounds, or me, who's about 160 pounds, we're going to have the same period if we start from that same small angle. But what will change the period of a pendulum? Well, on that swing set, I also have the high swings and I have the shorter swings for the younger kids. And those shorter swings, guess what? Well, they have a different period. You see how when I just shorten the string that my mass is attached to, it's going to go back and forth a little bit quicker. Whereas if I have a long string, it's going to take a long time to go back and forth. And so what we're getting at here is the longer the pendulum, the more time it's going to take to go back and forth, and that means that length, they do it with a little fancy cursive L on your equation sheet, is proportional to the time, or I should say, as the length increases, the time also increases, the period also increases. That does make sense. And so you're like, well, if it's not the mass on the pendulum, if it's not the weight of the person on the swing, then what is the other thing that affects it? Well, it turns out, this is pretty interesting. It turns out that it's, of course, the gravitational field strength, or wherever you are, whatever the gravitational field strength is, that's what's going to determine the period of the pendulum. And this has a cool little hidden meaning to it, right? Because that means that any pendulum on Earth, I can set it to a certain period, regardless of how much mass is on there, just by adjusting its length. So if you ever wondered how grandfather clocks all tell time the right way, well, guess what? They figured out what length it needs to be to oscillate back and forth at a certain period, and then therefore they can make that clock tick pretty accurately by using that pendulum. So those are the factors that the pendulum depends on. And here you can see, of course, the smaller the gravitational field. So if I would take this pendulum to the moon, right? Well, let's consider what actually causes this pendulum bob, we call it a bob, to go back and forth. Well, it would be the force of gravity pulling down. Look at the diagram I have here. You can see that mg is the restoring force, or rather a component of mg is the restoring force. Restoring force meaning the force that causes the object to oscillate, to go back and forth. In a spring oscillator, the restoring force is the spring. In a pendulum, the restoring force is that component of the force of gravity. And what determines the force of gravity? Well, the mass, but it turns out that because of F equals ma and the Fg equals mg, the masses kind of cancel out as far as determining the period of the pendulum, but the g does matter as far as how long it takes to go back and forth. You can imagine on the moon, everything kind of gets pulled down slower, so this thing would go back and forth slower. Or if I take it to Jupiter, which has a much larger gravitational field strength, it would pull it back and forth a lot faster. So that is why the period of a pendulum depends on the length and the gravitational field strength. All right, so I hope you got a conceptual overview. Again, I'm not getting into the nitty-gritty details of the derivation for this. I just want you to have a feel for what types of factors impact a pendulum or an oscillator's motion. All right, now we've talked about this word amplitude before. Amplitude just means the maximum displacement from the equilibrium position. So for a horizontal spring, that would be, hey, if this is where the system was at rest and I pull it back to its starting position or its farthest back part and then I let it go, that's called the amplitude. That's how far back I displaced it. For a vertical spring, all right, the amplitude is going to be how far it is from this equilibrium position here in the middle. Okay, the equilibrium position defined as the place where the force is balanced, or the forces are balanced. So in this case, for a vertical spring, it's a little different because in the equilibrium position, you actually have a spring that is already stretched, but the spring pulls up and the force of gravity pulls down, but they pull in equal amounts. And so because they are equally pulling in opposite directions, we're in equilibrium. That's why we call that the equilibrium position. So you can see for this little oscillator guy going up and down, as it swings through this red part in the middle, that's the equilibrium position. You can see it goes all the way up here and all the way down here, and those lengths are proportional, or those distances from the center, that amplitude, is the same on either side. Now for pendulum, the word amplitude gets a little shady sometimes. Sometimes people do amplitude as an arc length. Sometimes people do amplitude as an angle. Sometimes people do amplitude as a horizontal displacement from that bottom position. All right, now that can be a little confusing. The good news is they usually don't ask you too much about that. Sometimes you have to do a little bit of a math derivation if they give you an angle, and they might say like, hey, the pendulum is 2 centimeters from its equilibrium position horizontally, and they give you, maybe they give you some angle and they say, how long is the pendulum? All right, well, that's just a trig problem. That's not too bad, right? Because this is the opposite side and this is the hypotenuse. And if you know that angle, you can solve for that, the length of the pendulum. But usually when we talk about pendulum amplitude, we're just interested in how high above the starting point is it, because pendulum problems are actually energy problems, and even spring problems are usually energy problems. Energy being this potential energy, UG, and in that case, we're only concerned with that delta Y, how much higher above the starting point have we raised up. We don't really care, we don't have to get into the arc length stuff. We can just look at how much more energy does it have by lifting it than it did when we started. All right, so let's do a couple of quick practice problems to focus on this. I have about less than 3 minutes for this video, so I'm going to fly through these. All right, a grandfather clock has a period of 2. All right, so that means for a pendulum, TP equals 2. If only we could find some TP. Right now, I heard they're stocking back up. In one such clock, the pendulum bob has a mass of, don't forget to convert grams to kilograms, since this is AP physics, and all physicists use the SI units of kilograms. The pendulum is set into oscillation by displacing it 33 millimeters to one side. Oh, wow, that's really, really fun. I displaced it 33 millimeters. That doesn't matter at all, because when it says what's the length of the pendulum, let's consider the equation that we have. TP equals, sorry, I forgot my 2 pi out front here. 2 pi square root of, let me double check, I think it's m over k, and indeed it is. Oh, but it's not, because that would be the period for a spring oscillator, and we are looking at a pendulum. So let me erase that real quick for you guys. We're looking at the period of a pendulum, and I'll clean up my 2 pi there as well for you. All right, so 2 pi square root of, let's look for a pendulum, is L over G. All right, now you're like, well, what do we do to 33 millimeters? Answer, nothing. Right? Why? Because we know everything already. Look, the period of the pendulum is 2. All right, equals 2 pi square root of, oops. All right. Square root of L over G. All right, so we don't know the L yet, but guess what? It says that, well, I can assume, I think safely, that the grandfather clock is on the Earth, and that would make this G down here 9.8. And so all we have to do is algebra good to get the length of the pendulum out of this problem. So let me drop this in my calculator quick, and I'll just put the answer up on the screen for you guys. And if you type it in your calculator correctly and do your algebra good, your L turns out to be 0.9929, which I'm going to say is a pretty safe bet to call 1 meter. It turns out that a 1 meter long pendulum on the Earth oscillates back and forth with a period of 2 seconds. By design? I don't know. Let's see if we can get one more in here before the video ends. We'll go to the next problem. A pendulum, I'm going to skip that because we already did a pendulum one. Let's say we have a vertical spring. It oscillates with a frequency of, all right, frequency is 1.5 hertz. That means that the period is 1 over 1.5 hertz. You can go see lesson 1 for that one. And that is going to be 1 over 1.5. That's going to be 0.667. Got to round it so it's not evil. And it says that there is a mass of 0.1 kilograms on there. Well, you can see pretty quickly here that the T of a spring is 2 pi square root of m over k. All right, it says, what's the spring constant K? Well, we know the M and we know the T, so solve for the K. Answer.